Greetings, Dr. Lai. My name is Mama AIDIL IZHAM bin Asbobari with a matrix number of 24001-019, and today, for my KIB1016 video assignment, I'm going to present about the application of MOSFET in mechanomyography, also known as MMG sensor. So, let us first get an overview of what an MMG sensor is. An MMG sensor records the low-frequency mechanical vibrations produced by your skeletal muscles when initiating a movement. These vibrations are caused by the lateral oscillations of your active muscle that occur when the brain signals to make a movement. Much different to its counterpart, which is an EMG sensor. The EMG sensor mostly gets data by an electrical way. However, an EMG sensor first gets the data through a mechanical way, and then it translates it to an electrical data to be processed by the microcontroller. So let's see the characteristics of an MMG sensor. An MMG sensor records the data with a frequency range of between 5 to 100 Hz. It is mostly made by using an accelerometer, for example, an MPU 6050, and much difference to an EMG. It is quite non-invasive compared to EMG, which sometimes requires the patient to be inserted by some rods or electrodes inside their body to further increase the accuracy of the measurement. And like we mentioned before, an MG sensor uh, mostly deals with the muscle force and also the muscle fatigue. So now let us dive more into the architecture of the MMG sensor system, shall we? Like we mentioned earlier, the source of the data comes from the vibrations generated by the muscles when you are initiating any movement. And this vibrations is then measured by the sensor. In our case, let us use an example of an MPU 6050 accelerometer. An MPU 6050 accelerometer captures the movement of the vibrations of your muscles in a 3-axis way. This makes sure that no dimensions are missing and any single movement of the muscles is captured. And this measurement is taken in a frequency of between 5 to 100 Hz, which is your average frequency of your muscle. And after that, it is then sampled and processed in the integrated circuit of the MPU 6050 accelerometer to make sure that the data is clean and also translated to a way that can be read by the microcontroller. Now, talking about the microcontroller, let us use an example of an ESP32 here. The data from the accelerometer will then be processed to the ESP32, and this is when our MOSFET usually plays a big role at. And if you haven't known, most microcontroller usually comes with a built-in or an integrated MOSFET, and this MOSFET will play a critical role. And in our case here, the one that's most significantly is the GPIO drivers. And the GPIO drivers with the MOSFET will make sure that the the signal that we get earlier from the accelerometer is clean and is not and no signal is lost due to the special characteristic of the MOSFET, which will be discussed later. And it also will even smooth the signal at the same time. To understand how a MOSFET helps filter out any noise from a signal, we must first understand how a MOSFET even works in the first place. So, as you can see in this image over here, a MOSFET consists mainly of 3 parts, that is, the gate, the source, and the drain. As you can see in the picture, MOSFET are made mostly out of a P-type substrate, while the source and the drain is made out of an N-type. So ideally, we want these two to connect in order for the circuit to be complete. So how exactly are we going to get it to connect? Well, there comes the gate. Well, the gate is made out of an oxide layer. There is a silicon dioxide insulated between the gate metal and the semiconductor. And why so? This is to prevent any DC current. And why do we want to prevent it? As I mentioned earlier, to prevent any noise. So how does a noise relates to DC current? This is because the current that we will be getting from the accelerometer is actually quite small due to obviously the small and quite low movement of the muscles. Therefore, the data we will get is quite tiny. Therefore, if you if we were to even lose a bit of the current to this drop, then the data will going to be changed very significantly. Therefore, by applying this insulation, we make sure that there is no current that's gonna be dropped here. So you may be wondering, if you're not allowing current to flow, then how exactly is this thing gonna connect? Well, let me introduce to the concept of electrostatic. You see, even though the current is not flowing here, when there are electricity at the gate here at the oxide layer, it will uh, it will perform a electrostatic force that will cause it to be a static charge all over this plate. And as you can see, the plate is arranged to the point that the charge that will be generated is going to connect the two, the source and the drain. Therefore, the circuit will be complete, and that is how the circuit is connected while still not having any current drawn from the original signal. Wait, I know what you're thinking. Is this noise filtering even necessary in the first place? Is the noise gonna even affect the signal significantly? Well, surprisingly, it does. As you can see here, this is the difference between the raw signals that we got from the MPU 96050 just now versus the smoothed signal that only happens thanks to the MOSFET that we mentioned just now. So as you can see, yes, it is very quite significant, and imagine a slight change in that we're gonna affect quite a lot, especially in the biomedical field which involve the life of others. So we've looked on how AMG sensor work, so now let us see some of the few applications that they have in the real world. Much similar to its cousin, the AMG sensor, it is used in fields such as rehabilitation, for example, for marking the recovery of a paralyzed patient after the treatment. And how exactly? Well, like I mentioned earlier, it's gonna measure the muscle activity and compare it to a healthy individual muscle activity. Aside from treatment, also used in an analysis, for example, as a sport analysis, some very professional field will go to the point of analyzing the body performance of the athletes by using a, MMG sensor to make sure that it is in their top performance. So those are some of the applications of MMG in the real world. And thus, that concludes my presentation. May all of the information attained from this presentation be of good use. Thank you.